Hey, would you like to hunt for some little known but sometimes very rich types of gold deposits? They often carry with them silver and some base metals as well, making them really quite rich. When they erode, they can make placer deposits too, and in fact that's one of the ways of discovering them. Perhaps after watching this video and learning about these lesser known types of gold deposits, you'll go out and make a discovery at some placer deposit where nobody really knows what the source is. You'll go out and find it. The three types of ore deposits we're going to look at today are all associated with intrusive igneous rocks. That's rocks like granite or diorite, tunnelite, things that basically are a molten rock that intrude up into other rocks but never get to the surface to break out as lava. They cool below the surface and form crystals. But the heat from these bodies of rock can form different kinds of mineral deposits. And the three types of deposits we're going to look at today are all ones that are formed by this type of interaction. Now, the different kinds of deposits and what metals they have in them and what minerals make up the deposit vary somewhat depending on how deep in the ground the deposits form, what type of chemistry the body of rock has, and how close the mineral deposit forms to that hot body of rock. Some of them form quite close, some of them form a little further out, some of them form quite a ways further out. So they're all different, but they're all related to these bodies of intrusive rock. Hey, I'm Chris Ralph, the professional prospector, and today we're talking about three little known or lesser known types of gold deposits that are all associated with bodies of intrusive rock. And sometimes geologists call these bodies of rock plutons because it comes from way out deep in the ground. But that's the word that they use, plutons, for the body of rock. The three types of deposits are: one, skarn, and there are very much gold-rich skarns, but there are skarns for other metals too. Polymetallic replacement deposits, and these are deposits where literally the host rock is replaced by ore, and then polymetallic just means a lot of different metals. And then polymetallic vein deposits, again, lots of different metals, but instead of just replacing pods and chimneys of different types of rock to make ore, these are emplaced along faults or breaks in the rock and form what we would normally recognize as a vein. We'll start off by looking at the skarn deposits. They form the closest right up to the body of intrusive rock. The polymetallic replacement and vein deposits form a little bit farther out from the body of intrusive rock, but we're going to talk about, these are some very common different kinds of veins. So let me show you a diagram to help explain it a little further.
So here's a diagram of a number of different kinds of mineral deposits, and it's shown in what it looked like long ago and what the surface of the ground is now. So the green and the seawater at the upper level, that's where the surface of the ground was long ago. And then it's worn and eroded down, and you can see the brown line, that's the modern surface. And so I've circled the three types of gold deposits that we're going to look at in this video in purple, and the red pink kind of material in the middle, that's a body of this intrusive rock, a granitic type rock that's intruded into the ground, and then these deposits form near it. And the one that's just immediately to the right is the skarn deposit, and it shows a couple of different skarns. It says a proximal skarn, which forms immediately on the surface. It's a contact metamorphic deposit. And then the distal skarn, which forms a little farther away. And then further on the right, on the more distant, is the carbonate replacement or polymetallic replacement deposits, where it forms along favorable beds or along fractures. And then far to the left is the polymetallic vein deposit, which forms also a little further out from the intrusive rock. But both the replacement and the polymetallic vein owe their existence, as well as the skarn too, owe their existence to the heat and mineral fluids coming off of the intrusive rock in the middle.
Now, skarn deposits are a type of ore deposit formed by basically the interaction of hot, together with a hot body of cooling rock, water that may come mostly from the body of rock itself, but some from a meteoric water that's seeped down, and then also it forms by the heat and interaction of that in usually rocks rich in carbonates, which includes things like limestone or dolomite. It can be some types of shale that are rich in lime. So this is the kind of rock that forms skarns. And the type of rock that they form is this rock. It's called a skarn. It's an unusual kind of rock, and we're going to take a look at one in just a second. But they form and can be rich in iron, in tungsten, tin, copper, lead, zinc, molybdenum, and of course silver and gold. The term skarn, or sometimes geologists call it tactite, describes a special kind of rock that's formed from the interaction of these lime carbonate-rich rocks with the pluton, or the body of igneous rock that's cooling real close by. And the high heat that generates and water that's present in the system, magmatic water usually mostly, interact, and you can form this huge number of different kinds of metals. And skarns can be valuable for a lot of different metals, usually multiple different kinds. Skarns aren't called polymetallic, but basically they end up oftentimes being just that. There are two different kinds of skarn rock, one way more common than the other, and they're both formed though by this interaction of the hot from the cooling intrusive rock and the nearby carbonates and water. It's often coarse grained, and in fact I have a sample of skarn right here. This is a skarn rock. It has mostly garnet is what it's made of. The bulk of this rock is garnet. It has some calcite, which is your calcium carbonate that you would get from limestone. And it has a little tiny bit of epidote. Usually most skarns have a lot more epidote in them than this rock has. But then it has clots and chunks of molybdenite in it. It's the ore of molybdenum, and moly. And this rock, if I had a bajillion tons of it, a big deposit of it, it would be very valuable for the molybdenum that it contains. Unfortunately, the skarn that this came of was fairly small, really not much larger than the room that I'm in, which is to say one thing about skarns. They can range from really small, like the size of the room that I'm filming in, all the way up to half a mountain, or big, huge amounts. So there's all different sizes of skarns, and this one was particularly small, but it's rich in molybdenum. And I picked it up, like I say, when I was out prospecting in Nevada.
Here's a close-up of that rock I was just showing you, and you can see that pretty much everything brown on this rock, of which there's a lot, is garnet. Down toward the lower part of the rock in this picture, there's a white area with some dark gray, and the white is quartz, but the dark gray is the molybdenite, the valuable molybdenum ore. It's the chief ore of the mineral, or the metal molybdenum.
Okay, I mentioned that there's two types of skarn deposits. One is much more common than the other. It's called an exoskarn, and we're going to talk about that. Exoskarn means it's exterior, outside of the body of igneous rock, and basically it's a contact metamorphic type of situation because of the heat from the intrusive rock and any water that the magma contains, which is actually not really unusual that magma will contain some steam, and then reacting with lime-rich rocks like limestone or dolomite, something like that, it changes the rock next to it. And a changed rock, that's what metamorphic means, changed form. Meta is change, morph is form. So it's called contact metamorphic rock. And a lot of these rocks contain different types of ore deposits. The mineral deposits, the skarn rock, can be emplaced either along favorable bedding in the rock, or sometimes if there's faulting near where the intrusive rock has pushed through, it'll be emplaced along the faulting zones where it's been put in. And like I say, it forms in limestones or dolomites, which is another carbonate rock, or siltstones that are rich in carbonates, or sandstones rich in carbonates. It's always some rock that has significant amount of carbonate in the rock, because the carbonate can be dissolved and changed by any acidic liquids that come off the magma. The typical exoskarn minerals include a garnet, which, like I showed you, this piece had, this piece is like 90% garnet, but it can include other minerals like amphiboles, pyroxenes. Of course, epidote is a very common one. Zoisite, wollastonite, vesuvianite, magnetite, quartz, and of course, a variety of sulfides and oxide minerals. And the alteration of these contact metamorphic type rocks can introduce all sorts of variety of metals, including copper, zinc, lead, gold, silver, and others. That tungsten is another one that's commonly mined in skarn types of deposits. Let's take a look at some examples of typical skarn rock.
This is a piece of skarn from Montana. It shows the brown garnet like I showed in a previous specimen from Nevada, but it also shows a lot of green epidote, which my other specimen didn't show. This is actually from a gold-bearing skarn, but it doesn't show any visible gold in it. This is from a tungsten-rich skarn that's been mined in Nevada and shows much better crystals of garnet. It's not because better crystals because it has tungsten. It's just the way it formed. The crystals here are still, brown and flawed, but still better formed enough to be a decent specimen of garnet.
The second type of skarn rock is called an endoskarn, and it's actually quite rare. These are formed actually within the granite intrusive itself. So instead of forming in the adjoining carbonate-rich rock, it forms in fractures. It takes chemistry, it takes calcium and other things, magnesium, from the carbonate-rich rocks, and it does interact with the fluids, but the deposit occurs in fractures and breakages in the intrusive rock itself. And like I say, these are kind of rare and I won't go further into them, but skarns, the regular exoskarn that's more common, these are mined in many places for a variety of metals, and sometimes more than one metal at a time. Now, skarns that are rich in tungsten will have the mineral scheelite in them. Scheelite shines under black light. You can often see it, even though it's usually light colored and hard to distinguish, but if you shine a black light on it, it shows up pretty well. So that's one of the ways to prospect for tungsten skarns. We'll talk one of these days, I'll do a video about prospecting with ultraviolet light. And if you're interested in that, put a comment and say, hey, I'd really like to see that UV light video. Now, I mentioned tungsten skarns because tungsten skarns usually form at the very deepest level in the ground, the very highest level of heat, and the very closest level to the intrusive pluton. Copper and gold-rich skarns form a little higher up in the crust and form even sometimes a little bit of a distance away from the actual intrusive body. Sometimes they're so close to the surface they're actually considered almost like subvolcanic in nature, meaning the intrusive rock didn't quite make it to the surface, but it got close. Copper skarns are characterized by being rich in chalcopyrite, associated with magnetite and pyrrhotite. Some copper skarns, though not all of them, may have a significant amount of gold associated with the copper in the ore. Now, zinc-lead skarns also exist and are formed a little farther out from the pluton, and then they also can be rich in silver. Zinc-lead skarns are characterized by sphalerite and galena, often found in metamorphic rocks. But of course, the ones that we're interested in the most are the gold skarns. So let's focus now on the gold-rich skarns. Now, skarn deposits, valued primarily for their gold, are kind of considered by a geologist to be skarns that have at least 1 gram of gold per ton in the rock. But, that's considered decent open pit type of ore. And of course, they still have the distinctive skarn mineralogy. According to geologists, these gold-bearing skarns are usually calcium-rich exoskarns. Again, like I say, they're much more common, associated with very intense levels of alteration around the deposit, and they may also contain a variety of other metals in them, including lead, zinc, silver, of course, copper, even bismuth, and a number of other unusual elements, as well as the normal gold and silver. Now, native gold, pyrrhotite, base metal sulfide minerals, and even bismuth minerals are the most common minerals in gold skarns. Garnet, pyroxene, wollastonite, chlorite, epidote, quartz, actinolite, and other calcite minerals are common gangue-type minerals. Most gold skarns are found in island arc or orogenic belt mountain building belts, and or at least close to them, and are associated with the felsic to intermediate grade of intrusive rocks. The gold-bearing skarns may be hosted by a wide variety of different types of host rock, including limestone, dolomite, shale, conglomerate, even rhyolite to andesite tuff can be a host for gold skarns. However, an important amount of calcium, so calcite-rich like limestone, is usually present in the rocks that surround them. Like I say, ore minerals including native gold and electrum if the gold is silver-rich, chalcopyrite, arsenopyrite, sphalerite, galena, bismuth minerals, and such things as that. Occasionally tetrahedrite and bornite, marcasite, stibnite, and even tungsten or molybdenum minerals may be found in gold-rich skarns. I actually know of a skarn here in Nevada that was mined for many years for its tungsten, and yet some prospectors went out there and hunted around there in some of the dumps and some of the areas around the mine that were worked for their tungsten, and found some really, really nice crystalline gold specimens. And this mine had no reputation for producing any kind of gold. So with skarns, because like I say, they often have a variety of metals in them, you may be surprised what a skarn will yield. Now, that's not to say every tungsten-rich skarn, of which there are many, is going to produce some beautiful gold specimens for you. But there are some out there. That's what I'm trying to say. You shouldn't just automatically assume because it's a tungsten skarn or some other kind of skarn that there won't be any decent gold. Now, geologists have studied gold-rich skarns, and they often are fairly rich in grade, but often not that huge. A survey of different ones here in the United States were tallied, and they averaged about 250,000 tons, which for an open pit gold deposit is really not that much. 250,000 tons, but the average grade was 5.7 grams per ton of gold, and that's a really good grade for an open pit deposit. Prospecting indicators for gold skarns include placers in regions where there's no explanation as to why there's placer gold there. You may be in a rock type like a limestone or dolomite or something like that, where you wouldn't really expect to see gold placers, and yet there's a gold placer there, and no one really knows where the source of the gold is, and it may be one of these lesser known types of deposits, especially a skarn. Signs that will be associated with it is that samples of like the heavy materials in the stream are going to show elevated levels of bismuth and maybe some other unusual elements, even tellurites. Now, the placers associated with gold skarns usually aren't big, large, productive. They're kind of small and obscure, but the the deposit that's found with them can be really rich and well worth exploring and even mining for a larger mining company. Usually the gold that's found in these placer deposits is on the small side, fine gold, but sometimes coarser gold can be found in these deposits. Let's take a look at some examples of gold skarn ore so you can get a feel for what these types of ores look like.
Here's a map showing areas that would be favorable for gold skarns. You can see the darker gray. There's the black dots are well-known gold skarn deposits, and a lot of them are in this dark gray type of area. And the dark gray just indicates these are mountain building areas. The area in the western U.S., that's the mountainous part of the western states, going up into British Columbia and Canada, and even in South America, that's the mountainous western part of South America, and same with Europe and the Middle East there. But there are also some areas of the lighter gray that are favorable as well, shown as in the eastern coast of Australia, the eastern coast of the U.S., parts of Europe, and that sort of thing. So there are large areas that are favorable for potential gold skarn deposits. Here's a chunk of copper-bearing gold skarn, and you can see that the piece has some blues there because the copper has been oxidized to chrysocolla. It doesn't take very much chrysocolla in a rock to give it that color, but the color stands out and is easily recognizable. Here's some other chunks of gold skarn. Again, you can see the chrysocolla copper mineralization there that just makes the whole thing stand out, makes it real visible. These specimens are from the Yukon, are very typical for surface material. Here is a close-up picture of a small piece of gold ore it's gold skarn ore from a gold skarn deposit in Montana in the United States. And they've circled some little bits, little fine particles of free gold in the ore. And it's the erosion of these types of little bits that give rise to fine gold placers near deposits of this type.
Next, we're going to take a look at the polymetallic replacement deposits. Again, these are kind of related. They're formed in relation to these intrusive rocks, but they generally are further out from the intrusive body. And again, like the skarns that have lots of different kinds of metals in them, again, these polymetallic replacement deposits are polymetallic. They got lots of different kinds of metals in them. They often form in tabular, pod-like, or pipe-like types of bodies, and they're often rich in silver, lead, zinc minerals. And they can be localized by faults, or again, they can be emplaced along favorable bedding in a sedimentary rock. These deposits are found in various types of sedimentary rocks, but chiefly in limestone and dolomite types of deposits. And they're often formed when these types of deposits are intruded by porphyritic types of intrusions. The massive bodies of limestone or dolomite carbonate-rich rock will often fracture during the insertion of the intrusive rock, the pluton body. When it goes into a fracture, it breaks the rock as it moves up, and that becomes the thing that the breakage along there can be where the mineralized solutions flow and deposit these types of ores. Polymetallic replacement deposits often contain good amounts of galena for lead, salarite for zinc, and then various silver sulfur salts. It can be also silver dissolved in the galena, and so they have good values in silver. But they can also have decent values in gold, especially here and there in the ore body. There can be significant gold associated with the polymetallic replacement deposits. There's often some type of mineral zoning, which changes the nature of the minerals and metals present as you go from the closeness to the intrusive rock out to further distances. Jasperoid types of silicified rock are sometimes found in close association with these polymetallic replacement deposits. These deposits are formed by hydrothermal mineralized fluids that come off of the intrusive rock, emanating from intrusive and volcanic centers down below. And as the fluids come up, they're acidic and they interact with the carbonate-rich rock, and acids and carbonate rocks, acids will dissolve them. And so literally the acidic in the rock, the acid in the rock, the acid in the fluids literally dissolves the rock, and the ore body replaces the rock that was there. Sometimes ribbon-like or a blanket-like deposits will form in favorable beds. If maybe there's beds of non-soluble rock, but then a bed of limestone in between, so you'll get just the solution will go out in the limestone. Or sometimes, like I say, it'll go up along a fault and you'll get this pipe-like or pod-like type of form of this ore body. But it's normally doesn't form a very much clear vein-like thing because it doesn't emplace normally along a single fault crack. It'll be a broken rock zone or a favorable bed or that kind of stuff where it's replaced because the acid in the mineralized fluids dissolves the rock that's the host rock. Sometimes you'll get literally enough solution that there'll be caves of mineral-rich fluids, and you actually can get some really spectacular crystals in some of the caves that form by this replacement type deposit action. The types of deposits that these things are found nearby is usually basically base metal skarns. These are all associated type deposits, base metal skarns, polymetallic veins, like we're going to talk about next, but also porphyry copper type deposits will also give rise to these types of systems. Examples of these include Cerro Gordo in California and the Eureka District in Nevada. Some of you guys may have seen some of the videos about Cerro Gordo. My friend Jason Gaber went out and has done some work there. A guy bought the mine properties there, has been living there at Cerro Gordo at the old town site since, and has made a lot of interesting videos about that. So that deposit, the Cerro Gordo main deposit there, is of this polymetallic replacement type. Now, the ore minerals that are common in these types of deposits include galena, sphalerite, argentite, a tetrahedrite, which is a mineral that they find at Cerro Gordo. It's what gives rise to the copper blue types of stains there. Also, a chalcopyrite, bismuthite, proustite, perargyrite, jamesonite is another one, and gangue minerals include, of course, limestone, but also quartz, pyrite, and barite. Locally in these deposits, there can be rich areas of native gold and also rich areas of silver minerals. Sometimes they have tellurides, including a sylvanite and a calaverite. The ore deposits, the actual pods of ore, range from being very solid and to buggy to even just porous for the whole thing. They react with water that comes down from the surface. They're easily oxidized. And when the ore is weathered, it commonly is oxidized to, ochre types of, iron oxide deposits, but also cerussite, anglesite, hemimorphite, smithsonite, and cerargyrite. Let's take a look at both some sulfide versions and some oxidized versions of polymetallic replacement ores.
Here's a sample ore from Darwin in California. Darwin was a polymetallic replacement deposit with lots of lead, zinc, and silver. And you can see the galena in this, but there's been some oxidation. So you see some of the pyrite and other things have been oxidized to the rust color material. But this shows you what the flavor of the original ore was. Here's a big chunk of mostly galena from the Eureka district in Nevada. Eureka was a polymetallic replacement deposit that was very, very productive. It had a little more arsenic in it than most of the polymetallics, and then also had quite a bit of gold in it. It was rich in silver, but also rich in gold. And there were a huge number of ore bodies that were mined in the various mines near Eureka, Nevada. Here's a map of the ore bodies mined at Eureka, and shows some were quite deep as 900 feet were mined there, and quite a few. And again, it was one of the richest polymetallic replacement type deposits in all the United States. Here's some polymetallic sulfide ore from Pioche in Nevada, in eastern Nevada. This ore body was mined over a huge area that quite a bit was replaced. It didn't have very much lead, but it had a lot of zinc, a good amount of silver, and a small but significant amount of gold. Quite a bit of manganese also was found in the ore. Here's a chunk of ore from a polymetallic replacement deposit in Mexico, but it shows an unusual thing. Now, these ores, because they're sulfides, are very susceptible to oxidation if they're very near the surface. And originally, this would have been one giant chunk of galena, but the outer part of it, being exposed to rainwater and oxygen in the rainwater, has been oxidized to cerussite. So the kind of gray-brown material that's surrounding the material in the middle is cerussite. And then the core is still galena, the silvery material in the middle, the silvery blob. That's what remains of the original galena. And these ores are very frequently found oxidized if they're near the surface. Cerussite can come in massive and compact forms like you just saw, or it can be more crystals like this. I've even seen clear, colorless crystals of cerussite that have been faceted into gemstones. Now, sphalerite, the zinc mineral that's commonly found in these deposits, when it's oxidized, it turns to this, to smithsonite, or hemimorphite is another form of oxidized zinc. This specimen, a beautiful yellow-green color, was taken from Cerro Gordo in California. This is a picture of fairly coarse free gold on ore, zinc carbonate, which is smithsonite ore from Cerro Gordo. Now, some mines and some of these deposits, like Eureka, had a significant amount of gold in the ore. Others of them, even when they don't really have a lot of gold in the ore, may have pocket areas or parts of the ore that are very rich in free gold or silver too. This specimen is, like I say, an oxidized zinc area that was mined and shows some real nice coarse free gold. And Cerro Gordo, though, was not really known for producing very much gold.
Next, we're going to talk about polymetallic vein deposits. These belong in the same group, and polymetallic vein deposits are formed when mineral-rich fluids migrate through well-established fractures and faults and form vein-type deposits, veins of the nature that we're well used to with different types of veins. The mineralizing fluids go through these veins. They may react with the wall rock or not, depending on what the wall rock is, but they deposit all kinds of sulfide minerals and then various gangue minerals that go with them. As implied by the name polymetallic, they contain often a number of different kinds of metals, and they are worked for metals including lead, zinc, copper, silver, and of course sometimes gold. The metallic minerals are often in the form of sulfides or various sulfur salts, sometimes oxides as well. And the polymetallic deposits, like I say, form through the heat and magmatic fluids coming off of a body of intrusive rock and then coming up through established fault zones and faults, and then depositing in that fault zone, in the fracture zone where the mineral fluids can circulate as it reaches toward the surface and cools down. Various types of minerals, both metallic minerals often as sulfides, and then also gangue minerals like quartz or calcite, fluorite, and others. These types of veins are generally belong to the silver, lead, zinc category, but they can have other metals, including antimony. They often have gold and silver, significant values in gold and silver. When I was a young, freshly minted graduate from the Mackey School of Mines, a newly minted engineer, I worked at a vein deposit, a polymetallic vein deposit in central Nevada in the Candelaria district, and the vein had significant lead and antimony. We weren't really interested in the lead or antimony, but we were interested in the gold and silver that were in the rock, and so we did cyanide leaching to extract the gold and silver. The intrusive rocks that are usually associated with these may be a ways off. A lot of times, even in some districts, there's not even any exposed intrusive rock. You may find that the intrusive rock is down so deep and so distant that there's nowhere at the surface that it's exposed, but you have these type of veins that tell the geologist that there's these types of intrusive rocks nearby. The intrusive rocks that form these are generally they're felsic rocks, meaning they're more acidic than basic, and they range from diorite to granodiorite and monzonite to monzogranite. They're usually in that kind of category. The polymetallic vein is really the most common of the different intrusive related mineral deposits. Of these types of deposits, it's the most common one. The vein structure can be complex with a number of different branching veins. They can also have multi-phase types of where there'd be a time when the mineralizing fluids deposit one thing, and then later the mineral fluids deposit something else, and so you get this kind of multi-phase, different metals in different areas type of a system. And the surrounding rock generally has an envelope of sericitic or argillitic alteration that kind of surrounds the vein. Tetrahedrite or tenetite is one of the characteristic minerals in a lot of these types of veins, although the one that I worked at when I was newly minted fresh out of school, that was a vein that was really more lead, antimony, silver, gold, and not very much copper. A little tiny bit, not much. Other sulfide minerals that you might find in these veins include sphalerite, galena, chalcopyrite, jamesonite, which jamesonite was the principal lead silver mineral at the mine that I worked at. Jamesonite is a lead antimony type of sulfide mineral. But these deposits can also have native bismuth, stibnite, and even arsenopyrite, but it varies depending on the chemistry of the vein, what type of deposit you'll have. Most of these veins were mined principally for their silver, but often the lead and zinc were recovered as well, as it was shipped to a smelter. In various places, and like I say, especially the mine that I worked at, the gold values were also important. And so native gold and electrum can be present in some of these veins. Many of the smaller veins in some of the districts are worked, they're worked on a real small scale, or worked principally actually for their gold content and only secondarily for the silver. Scheelite can also be present in some of these veins, which is a tungsten mineral as well. In a very few of the veins, actually the scheelite was the principal mineral that they were mining. So like I say, all of these polymetallic vein deposits are related to intrusive rock activity. These polymetallic veins are, like all of the different types, the three types that we're looking at today, related to intrusive rock activity. And so they're kind of associated. It's not unusual that polymetallic veins will be near porphyry deposits, which are another type of intrusive related, or near skarns, or near polymetallic replacement types. So the polymetallic veins are very common, and they're found in close association with some of these other types. Geologists point out that a lot of times these polymetallic vein type deposits are found in association with porphyry copper deposits or other intrusive centers where you have intrusive activity that's mineralized. And so you'll get a series of these different kinds of deposits. Because polymetallic veins can have significant gold in them, it's not unusual that distant from a porphyry copper deposit, you may have a placer gold deposit that forms, and it's formed from erosion of these polymetallic vein deposits. There's examples of this. The Bingham Canyon deposit in Utah had some really rich placers associated with it, but they weren't where the porphyry copper is. They were nearby, and actually the dumps from the big porphyry copper mine have buried all the area that they used to mine for placer gold. There are also areas in Arizona where there's placer gold that's associated with porphyry copper deposits, and they're mostly these polymetallic veins. And a lot of times, they're placer deposits and they're probably associated with these veins, but there may be little or no exploration of the vein type deposits itself. So it may be worthwhile to go out there with a metal detector, especially if it's coarse enough gold that the miners were recovering it as placer. It might be worth going out there with a metal detector and seeing if you can't find the vein source where the gold is coming from. Now, the minerals in the polymetallic, especially the gangue minerals in these polymetallic vein deposits, kind of record for geologists their temperatures and pressures of formation. And what it shows is that these things are often intermediate between skarn types, which are high heat types of deposit, and epithermal, which are lower types of deposits, a lower temperature types of deposit, but also ones that can be very rich in gold and silver. The depth of formation for the polymetallic veins is usually about 2 kilometers. So, in the range of a mile plus. That type of depth, which is usually a little more deep than is typical for an epithermal type of deposit. Now, I have done a video on epithermal deposits, epithermal gold and silver, and if you want to also check that video out, I'm going to put a link up above to it, and you can go check that one out. It's been very popular. Epithermals are some of the richest gold, silver deposits, especially in Nevada, but also in other adjoining states. Now, polymetallic veins can be distinguished from the epithermals by their closeness to these intrusive rocks and by their association with skarns or polymetallic replacement or even porphyry copper types of deposits, and their occurrence in usually non-volcanic types of, usually sedimentary types of rocks, but sometimes metamorphic, not volcanic rocks, which are most common for epithermals. Additionally, the polymetallic vein deposits almost always carry significant more base metals in them than would a typical epithermal type of deposit. Let's take a look at some examples of polymetallic vein ore, and we'll take a look at that so you can know what these ores look like.
This is a piece of jamesonite. It's a lead antimony sulfide, and it was the primary ore mineral, or at least the ore mineral that formed when the vein was formed at the mine that I first worked at when I got out of school. This is a specimen of galena with some yellow pyrite, and the white is calcite. This is from a polymetallic vein type system, and galena is a very common mineral in many polymetallic veins. The dark colored mineral here is sphalerite, which is a zinc sulfide, another very common mineral in polymetallic veins. The lighter colored yellowish material is pyrite. The dark colored metallic mineral in this sample is tetrahedrite, which is a copper antimony sulfide. And then the white or light blue colored chalcedony is actually colored light blue by the copper. This is an actual chunk of polymetallic vein ore. The gray is galena in here, and then the dark, almost black color is silver minerals, almost certainly argentite, acanthite type rich silver. This is a copper-rich polymetallic ore. The yellow is chalcopyrite, and the green is actually stains of malachite from a small amount of oxidation of the ore. Because these veins are rich in sulfides, they're very much subject to oxidation by groundwaters with oxygen in them. And this is from the mine that I first worked at when I graduated from the School of Mines. And it's bindhemite, which is a lead antimony oxide, and it comes from the oxidation of jamesonite, which is a lead antimony sulfide. Lead will usually oxidize either to cerussite or anglicite, which are minerals that are more common, but sometimes it oxidizes to lead oxide, which is the yellow in this specimen here. Now, when galena oxidizes, like I say, it usually forms either anglicite or cerussite, and the light color with the brown on this one is anglicite. It once was galena, but it's been oxidized by the effect of water with oxygen in it. Now, a lot of times galena has silver in it, in the literal molecules of, or the atoms of silver will replace and take the place of the atoms of lead in the galena crystal structure. But when it oxidizes, they no longer are able to mix the same way, and they separate. And this is actually a natural separation where it once was all galena, and now we have anglicite, the lighter colored, and then chlorargyrite, which is a silver chloride on the left-hand side. That's more of a gray and yellow kind of specimen. So this is rich silver ore on the left, and then oxidized lead ore on the right.
So all three of these types of rocks that we're looked at today, the different types of deposits that we've looked at today, are all associated with bodies of intrusive rock that have come up to near the surface and provided mineralized fluids and heat to drive a system of formation of veins or replacements or skarns, something like that, that has the valuable minerals in them. Now, the first two are almost always found associated with carbonate rocks. The polymetallic veins can be found in carbonate rocks, but also often in metamorphic rocks, and only very, very rarely in volcanic rocks. Good places to look for these types of deposits, I've kind of hinted at it, are places where you have placer deposits that form and maybe are known, maybe they were little known placer deposits, small placer deposits that people just don't know where's that gold coming from, and so they haven't figured it out yet. And because these are lesser known and not so much recognized by the old time prospectors, those kinds of areas are good places to look for these types of deposits. And you can go out there and test the gravels and see what kind of minerals are associated with the deposits, and they'll kind of give you a hint. Is it got a lot of garnet in there? Well, maybe that's a skarn type. So anyway, there's also various things that you can know about these deposits, and when you test it and go look for these, I wish you the best of success, because I think there's a good opportunity here for prospectors. Now, prospecting is a skill and it takes knowledge. I mean, I've done a fairly technical type of video today. I've done a number of these, and they seem to be well appreciated. And what makes all the difference in your success in prospecting. If you go out there and don't know anything, your chances for success are less. And what I did in addition to these videos is I wrote a book. It's called Fistful of Gold, because that's what I want you to be able to go out and get, is Fistful of Gold. And I'm going to tell you a little bit more about my book, because my book is intended to impart to you the knowledge and skill that I've gained in 40 years of prospecting. So I'm going to tell you a little bit more about my book right now. So this is my book, Fistful of Gold. You can see it's an encyclopedia distilling down my 45 plus years of prospecting experience plus my degree into the parts that you need to know. I spent most of 10 years writing this. It was not just a simple effort that I sat down and wrote it. You can see it's like 250,000 words. It's not something you're going to read through in a day or maybe even a week or more.
but it's got a lot of information and reference material that you can come back to. You can read it once and read it again and get more out of it because there's just that much depth of material in this. I wrote this book because I want you to have the skills to go out and find fistfuls of gold for yourself. And if you have the skills and know what you're doing and get out in the field and make a real effort, you can find significant gold. It's not easy. I'm not going to tell you that because, gold, it wouldn't be, close to $2,000 an ounce, which is what it is right now. It wouldn't be so expensive if it was easy to find. It's not easy. You just can't walk out into an old gold field and start picking up nuggets. If the gold was easy to see and find, the old timers would have picked it up and taken it themselves. So you got to have skill. You got to know what you're doing. You got to be able to master what it takes to find gold, and you've got to have the persistence and put in the effort to find the material, to find the gold or diamonds or gemstones that you're looking for. Now, this book has geology, it has facts about gold, it has stuff about diamonds and platinum, but it's mostly about gold deposits, how gold deposits form, how placer and nuggets form, all the questions you probably wanted to ask. The book is available on Amazon, and I'll put a link to it in the description below, but you can look up on Amazon, Fistful of Gold, and by Chris Ralph, and find this book. Now, the book, if you look on it, it has a very high rating. It has like a 4.7 or 4.8 out of 5, which is really high. I mean, it's hard to please everybody, but I'm close to a 5 out of 5, not far from it, right? So it's been out. I've sold more than 15,000 copies of this book, and I've had tremendous response, tremendous positive response by the people who buy it. And I think if you buy it, you'll be just as happy with it. Now, in addition to my book, I also have a website that I do, and I'll tell you a little bit more about my website and show you some images from the website right now.
Now, my website is nevadaoutbackgems.com, and I'll put a link to the prospecting page, this prospecting encyclopedia page, down in the description below, but you can find it at Nevada Outback Gems. I sell some jewelry, turquoise, other gemstones there. I don't always keep the inventory perfectly up to date, so if you're interested in anything you see, do contact me first before trying to send me money or anything, because I want you to be able to get what you order. But the website has lots of different stories, old adventures, even some stories, true stories from the old-time miners of the 1800s. So I think it's something you'll find interesting.
The other thing I want to go back to is that all my comments, I want you guys to ask questions on the comments for my videos. I answer 100% of the comments that are made on my videos. Now, sometimes if somebody just says, hey, great video, I really enjoyed it, the comment may just be, well, I'm really glad you liked it. Or if it's a simple question. And sometimes I get people who ask me questions, I would take a book to answer that question. And I recommend that they just buy the book. But I answer all my questions. I try to help people as much as I can. I'm here to help you. So if you're interested in gaining the skills, if you're interested in knowing what you need to know to be successful, follow along with me. Subscribe to my channel, hit the bell so that they'll let you know when I come out with new videos, and I try to do that pretty much every Saturday morning. And you'll enjoy with me, you'll come along with me, we'll have an adventure together, and we will find some nice gold and see what it's really like getting out in the woods, or the deserts, or the mountains, wherever we land, wherever the gold is, wherever the diamonds are, wherever the platinum is. Come along, we'll have some fun. And I'll see you real soon on the next video.